Okay, good day everyone. Okay, so today this will be our part 3 of our discussions about kinetics, specifically work and energy. Okay, um, in the last two videos we have discussed about work and the formulas regarding the law of conservation of energy, which includes equations of uh, kinetic energy, which includes the kinetic energy, potential energy, and work. Okay, and we also have talk about uh, conservative and non-conservative forces. So in this video, we will going to have a summary of those formulas. Okay, we will going to have a summary of uh, formulas. Okay, that are not explained well in those first two videos. Okay, so I have not mentioned maybe your kinetic energy. Okay, okay, so our kinetic energy, okay, just a review. Okay, kinetic energy can be denoted as either KE or T. And then for potential energy, it is usually denoted as, in some references, it is denoted as PE or also as V. And then your work could be denoted as either W or U. Okay, so these three, okay, may be used. So if you use denotations of key, PE, and W, so you use this in unison. Okay, not to mix with the denotations T, V, and U. Okay, so so kinetic energy, potential energy, and work can be either denoted as K, PE, and W, or if you are not in the book of R.C. Hepler and other references, instead of these three, we use T, V, and U respectively for these three. Okay, so that is how we denote kinetic, potential energy, and work. Okay, so just a review. So under work, we have these following formulas. Okay, so so if your forces is traveling a straight path or straight horizontal path, we use this formula in which your work, or your, let us denote first as W. Okay, so your W or your work is equivalent to your force times S2 minus S1. Okay, so okay, so your S1 is the initial position and S2 is the final position. Okay, so from the definition, your work is equivalent to force times displacement. Okay, so makes sense because the difference between two positions is equivalent to displacement. Okay, so as we have you have learned in your kinematics. Okay, work equals force times displacement. And then we have, okay, so we can use okay, so if okay, so this is for straight horizontal path. Okay, so what if it's not a horizontal path? Okay, so let us say it is an erratic path, or let us say erratic which means that it may have a general motion like this. So it will have move in an erratic manner, or let us say curvilinear, or in a general motion. Okay, so we can say erratic, curvilinear, or general motion. We can use these following formulas. Okay, so you can use, okay, your W. Okay, so this W can be also denoted as your U. Okay, so we can say W. If you use W, if you want to use W, or you want to use U as a symbol of work, so you use U. So W equals to U is equal to F times S2 minus S1. So for erratic or curvilinear general motion, so given that your any position at that time is at a certain angle with the horizontal, so you can use W or U. Okay, let us say is equivalent to, okay, F cosine theta, okay, times the displacement, which is S2 minus S1. Okay, so you can also denote this as U. Okay, so in the book of Hebeler, okay, so it is usually denoted as U. Okay, so it is F cosine theta times the displacement, or the change in position, S2 minus S1. Okay, so you can use that. And okay, so in a general term, okay, so we can denote your U. Okay, so your U for position 1 to 2. Okay, so this is also can be denoted as U 1 to 2, or W 1 to 2. Okay, so we are speaking of position 1 to position 2. Okay, so you can also denote this one. Okay, U or W is to 1 is to 2, 1 point 1 to point 2. So your formula here in terms of integral is equivalent to F, okay, ds, or S2, okay, lower limit S1 and upper limit as S2. Okay, so this is the solution if you use a graphical method. Okay, so you can use any of these formulas depending on the situation. Okay, so but somehow there is also what we call work by okay, this is what there is also what we call work by work caused by weight. So your work caused by weight is equivalent, okay, let us say UW is equivalent to your weight negative, okay, negative weight times Y. Okay, or the change in, or more accurately by the change in Y. So if the object, okay, so from position 1 then travel to position 2, okay, so there is a change in position. Okay, so if this object starts at point 1 and then to 2, and there is a change in displacement relative to y-axis, okay, or the vertical, so you use this formula. Okay, so for kinetic energy, okay, So when we say kinetic energy, we denote it as stored energy. And stored energy, okay, we can denote it as Ke. Okay, so it is equivalent to 1/2 mass times velocity squared. Okay, this is something that I have not discussed last two videos. Okay, so I'm sorry. Okay, so I just like to clarify, your Ke is equivalent to 1/2 mv squared. Okay, so you can also denote from our book, Ke can be also denoted as T. So your T is 1/2 mv squared. Okay, so this is applicable for, okay, non-conservative forces. Okay, this I for conservative forces, I mean, okay, conservative, okay, forces. Okay, so if we say non-conservative forces, so it will cause work inside your system. Okay, and then we have potential energy. When we say potential energy, okay, so if you have an original position at 1, and then it is elevated from the ground at y, so your potential energy PE is equivalent to the weight. Okay, so not to be confused, this should be, okay, mass times gravity, so that you will not be confused. So mg times the change in y, or your mass times the acceleration due to gravity. So this is mass times acceleration to gravity, or mg times y. Okay, so you might be confused with work caused by weight and potential energy. Okay, the relationship between the work, okay, specifically the work caused by weight, or the conservative force, is the negative change in potential energy. Okay, so or PE, okay, or negative, it could or negative PE sub 2 minus PE sub 1. Okay, and if we denote 1 and 2, we can okay, so we can derive the relationship between potential energy and your work caused by weight. Okay, so I hope this have closed, okay, some issues, some important topics, important knowledge you should have in order to full uh, understand work and energy in kinetics. Okay, so we talk about concept first in this third video. Okay, so from part 1 to part 3, we talk about the concepts. Okay, so in the next video, we will have, don't worry, because we will be solving problems involving work and energy, so that you will understand better uh, these formulas, and when will we use these following formulas. Okay,